Now that we've looked at the basics of probabilities, we're going to look at some more complicated cases when we have experiments that involve more than one step. And we're also going to look at some ways to organize that information. So just a reminder that probability is a topic that is first discussed in detail in 7th grade in the Common Core State Standards. Let's imagine we're asked to play a game, and this is a two-player game. Each player gets a board that looks like this, containing the numbers 1 through 6, and each player gets 12 chips to put on the board. They can put the chips anywhere, but they also have a die to roll. So the players take turns rolling the die, and as they roll the die, whatever number comes up, they're allowed to take a chip off of that number on the board if there is a chip on that number. And the first player to remove all of their chips from the board wins. So you might want to think about a strategy for a game like this. Since we're rolling one die, and the probability of getting any one of the rolls on that one die is 1/6, you might think that because we have equally likely outcomes, a good strategy for the game might be to just put 2 chips on each of the numbers so we're equally distributing the chips, and that actually would be the best strategy for this game. Now what if we make the game a little more complicated and we give each player a board that has the numbers 1 through 12, and we still give them 12 chips, and we ask them to distribute the chips onto the board so that when they roll, in this case, 2 dice, and they add the numbers on the dice, that they can remove a chip that's on that number. So what would the best strategy in this game be? Well, maybe you might be thinking, well, with 12 chips and there's 12 numbers, so let's just put 1 chip on each number. Well, as it turns out, that's not really the best strategy for this game. In fact, we've already looked at this sort of problem when we made a table to find all of the outcomes that we have when we roll 2 dice and we look at their sums. And if you think about the outcomes, you can see that not all of the possible outcomes happen with equal probability. For example, there's only one way to get a 2, that's to roll a 1 and a 1, but there's 6 ways to get a 7. A 6 and a 1, a 5 and a 2, a 4 and a 3, a 3 and a 4, a 2 and a 5, and a 1 and a 6. So these 12 numbers we've been given on the board aren't equally likely. So to put 1 chip on each number doesn't make any sense. In fact, it doesn't make any sense at all to put a chip on the number 1. So if you wanted to distribute these chips, you might decide to put more of the chips on the numbers that are more likely, like the 6, 7, and 8, and put fewer chips on the numbers that are less likely. So that would probably be a better strategy for this particular game. So let's think about a different type of probability experiment. Let's suppose we have a spinner that has blue and red and yellow on it, and each of those colors are equally distributed on this spinner. So what if we're going to spin the spinner and we want to look at all of the possible outcomes if we spin the spinner twice? So we need a way to organize this information. It's a multi-stage experiment because we're spinning the spinner a first time, that's the first stage, and then we're spinning the spinner a second time, that's the second stage. So one way we could organize the information is basically the same way we did when we were rolling 2 dice. We could say that there's a first spin and there's a second spin. The first spin and the second spin could each have red, yellow, or blue with equal probability. And then if we combine those spins, so for example, if we spun 2 reds, we could call that red, red. Or if we spun a blue on the first spin and a red on the second, we could call that blue, red. Or a yellow on the first spin and a red on the second spin, we could call that yellow red, and we could do that for the entire table, and we can see that we've got 9 possible outcomes for this experiment. So if we wanted to list all of those outcomes, we could just abbreviate, and we could list them as red, red, blue, red, yellow, red, and so forth until we list all 9 outcomes. So each of these 9 outcomes are equally likely. So what if we want to know the probability of getting blue on exactly one of the spins? Well, we have these 9 equally likely outcomes. All we have to do is find all of the outcomes in which blue happens exactly once. And there are 4 ways that we can do that. So the probability of getting blue on exactly one of the spins is 4/9. So let's look at another way we could organize this information. We can draw what's called a tree diagram to represent the outcomes that we have in this multi-stage experiment. So here's how we do that. When we draw a tree diagram, we think about a starting point. And then from that starting point, we think about what happens in the first stage of the experiment. So the first stage would be to spin the spinner for the first time and either spin a red, a blue, or a yellow. So from the start, we can either spin red or blue or yellow. So each of these line segments that you see drawn are called the branches of our tree. Now if you look at the very first branch on that tree that leads to red, that would mean on the first spin we spun a red, but now we have to have a second spin. So if the first time we spun a red, the second time we can still spin a red or a blue or a yellow. So we'll show branches to indicate that if we get a red on the first spin, we can get any of those 3 possibilities on the second spin. Now if you go back to the first spins and you find the blue, if we spun a blue on the first spin, we could get a red or a blue or a yellow on the second spin. And if you go all the way down to yellow on the first spin, if that's what happened, we could get a red or a blue or a yellow on the second spin. Now if you follow the branches from the start to the end of each branch, you'll find all of the outcomes. So if you go along the top branches, that would be a red on the first spin and a red on the second spin. If you go on the second set of branches, that would be a red on the first spin and a blue on the second spin. And we can continue that all the way down until we have all 9 outcomes ending at the bottom with yellow on the first spin and yellow on the second spin. So if we answer that same question, find the probability of getting blue on exactly one of the spins, we're going to do it exactly the same way we did with the table. We have our 9 equally likely outcomes. We're going to look to see which of those outcomes have blue on exactly one spin. So that happens in 1, 2, 3, 4 ways again, so that probability is still 4/9. So there's a multiplication rule we can use for probabilities, and it goes like this. If we have a multi-stage experiment and we want to know the probability of outcomes along any path in the tree diagram, then that's equal to the product of all the probabilities along the path. Now this can be a really interesting thing to be able to use if we have probabilities that are not equally likely along the paths of the tree. Now let's look back at this spinner that we're spinning, and let's find the probability of getting blue on exactly one of the spins. But we're going to look at this a little bit differently. We're going to draw the tree slightly differently. So what we want to know about is how can we get a blue on exactly one spin? So we're going to break this down into thinking of either getting a blue on a spin or not getting a blue. And we'll draw our tree that way. So on the first spin, we either have a blue or we have something that's not blue. Now, the probabilities we have for each of these things are not going to be the same, because if you look at the spinner, there's one of the three equal pieces that's blue and two of the three equal pieces that are not blue. So if we think about the probabilities of getting blue or not blue, they're not going to be equal. In fact, the probability of getting blue is 1/3 and not blue is 2/3. So let's suppose we get a blue on the first spin. On the second spin, we could still get a blue or something that's not blue. And once again, the probability of getting a blue is 1/3 and not blue is 2/3. If we don't get blue the first time, then on the second spin, we can either get blue or not blue, and once again, the probability of getting blue is 1/3, and not blue is 2/3. So, let's use that multiplication rule for probabilities. We want to know the probability of getting blue on exactly one of the spins. Well, that doesn't happen here. Getting blue and blue would be getting blue on exactly two of the spins, but the probability of that happening is equal to the probabilities along the branches, which is 1/3 times 1/3 or 1/9. Now if you look at the second path, that goes through blue on the first spin and then not blue on the second spin. If we multiply those probabilities along those branches, we have 1/3 times 2/3, which is 2/9. So the probability of getting blue on the first spin and not blue on the second spin is 2/9. If you go along the third path that we can choose, that would be not blue followed by blue. Those probabilities multiplied together are 2/3 times 1/3, which is 2/9. So the probability that we get something that's not blue on the first spin and then blue on the second spin is 2/9. And then at the very bottom, we have a path that goes through not blue and not blue. The probabilities along those branches are 2/3 and 2/3. And if we multiply those probabilities, we get 4/9. So the probability of getting not blue on the first spin and not blue on the second spin is 4/9. But we want to know the probability of getting blue on exactly one of the spins. That happens here when we get blue on the first spin and not blue on the second. And it also happens here where we get not blue on the first spin and blue on the second spin. So we can get one or the other of those possible things happening. So the total probability of getting blue on exactly one of the spins is the sum of those probabilities. 2/9 plus 2/9 is 4/9. So when the occurrence of one event has no influence on the outcome of the second event, the two events are called independent. That's actually what we saw going on here. If we spun, let's say, a red on the first spin, it had absolutely no effect on the second spin. The second spin, we could still get the blue, the red, and the yellow with equal probabilities. So the first spin's outcomes and the second spin's outcomes are considered independent of each other. They have absolutely no effect on each other. So let's look at this question. A multiple choice quiz contains 3 questions, and each question has 4 answer choices. What is the probability of getting exactly 2 questions right by random guessing? So let's think about what a tree diagram would look like for this. We need to answer the first question, and the first question is either right or it's wrong. Now, if each question has 4 answer choices, that means that there's only one way we can get the first question right, and that's to answer in the 1 out of 4 ways that make it correct. So the probability that we get the first question right is 1/4, and the probability that we get the first question wrong is 3/4. There are 3 out of the 4 choices we can pick that are wrong answers. Then we answer the second question. Now the second question is either right or wrong, And whether we answered the first question right or wrong has absolutely no effect on whether we answer the second question right or wrong. So the probabilities aren't going to change. We still have a 1/4 chance of getting the first or the second question right and a 3/4 chance of getting it wrong. If we answered the first question wrong, we can get the second question either right or wrong. Once again, the probabilities aren't going to change. And the third question's outcomes are independent of the first and the second question's outcomes. So once again, we can either get the third question right or wrong, and the probabilities of getting the third question right or wrong aren't going to change from the probabilities of getting the first or the second question right or wrong. So we're still going to have a 1/4 probability that we get the third question right and a 3/4 probability of getting the third question wrong. So what are the possible outcomes? Well, if we follow the paths from start to finish, we could get all 3 questions right, or the first 2 right and the last one wrong. And if we keep following all the paths down to the bottom, we'll see the last outcome is getting all 3 questions wrong. Now what we want is the probability of getting exactly 2 questions right. So if we look at all of our outcomes, we can find all of the outcomes where we get 2 questions right and 1 question wrong. That happens in these 3 possible outcomes. And if we follow the probabilities along those branches and multiply them together, so for right, right, wrong, that would be 1/4 times 1/4 times 3/4, which is 3/64. For right, wrong, right, that's 1/4 times 3/4 times 1/4, which is 3/64. And for wrong, right, right, that's 3/4 times 1/4 times 1/4, that's 3/64. So the probability of getting exactly 2 questions right by random guessing is the sum of the probabilities, which is 9/64. So it's not a very good chance that we're going to get 2 of the 3 questions right. So let's make this test a little bit longer. What if we have a multiple choice quiz that has 10 questions and each question has 4 answer choices? What's the probability of getting all of the questions right by random guessing? Now with 10 questions, we probably don't want to make a tree because that tree would get to be very complex. So if we had this to begin with and we took it out to 10 questions, we would have so many outcomes in the end. It would become very unwieldy. But what we need to think about is that we're looking for the probability of getting all the questions right, which means if you look along the very top branches here, where we get the first question right and the second question right and the third question right, we would really just be extending that all the way out to 10 questions, which means we would be multiplying 1/4 times 1/4 times 1/4 10 times, which is 1/4 to the 10th power, or 1 over 1,048,576. So the probability that we get all 10 questions right by random guessing is very, very small. Here's another multi-stage experiment. A random ball is taken from box 1 and placed in box 2. Then a random ball is taken from box 2. What is the probability that the ball taken from box 2 is red? So let's make a tree diagram to describe what's going on. Remember, the first thing we're doing is taking a ball from box 1, and box 1 has white balls and red balls in it. Now if we just look at box 1, the probability that we take a white ball from box 1 is 3/5, because 3 out of the 5 balls are white. And the probability of taking a red ball out is 2/5. So once we've taken a ball from box 1, we're going to put that ball in box 2. So let's suppose that the ball we took from box 1 is white. That ball is going to go into box 2. So now if we look at box 2, it has 5 balls in it. Some are white, some are red. 4 of the balls are white and 1 of the balls is red. So we have a 4/5 probability of choosing a white ball and a 1/5 probability of choosing a red ball. So let's go back to where we were. We had 3 white balls and 2 red balls in box 1. What if we chose the red ball from box 1? That would get put in box 2. Now box 2 has 5 balls. Some are white, some are red. But the probabilities are not the same as they were along the top paths of the tree. Because now we have 3 out of 5 that are white and 2 out of 5 that are red. So what we're looking for in this problem is the probability that the ball taken from box 2 is red. So let's take a look at the probabilities along the branches. The top branches give us the probability of getting 2 white balls. That's not really what we're interested in. The next set of branches would be getting a white ball and getting a red ball, so we'll multiply those probabilities along the branches. That's 3/5 times 1/5, which is 3/25. And that would be a possibility where we get a ball from box 2 that's red. The next set of branches is getting a red ball, then a white ball. Those probabilities multiply to give us 6/25. That's not what we're interested in. We want to have the probability that the ball taken from box 2 is red. That would be taking a white ball from box 2. And then finally along the bottom branches, that would be taking a red ball from box 1 and then a red ball from box 2. Multiply those probabilities. 2/5 times 2/5 is 4/25, and we are interested in that probability because that would be pulling a red ball out of box 2. So the two probabilities that we are interested in where we get a red ball out of box 2 are these two. If we sum those probabilities, we get 3/25 plus 4/25, so 7/25 is the probability that the ball taken from box 2 is red. So let's stick with a problem where we're taking balls out of a box, but this is a slightly different one. A random ball is taken from this box. Then, without replacing the first ball, a second ball is taken from the box. What is the probability that both balls taken from the box were red? Now we can draw a tree for this. So the first time we take a ball out, it's either white or red. 3 out of the 5 balls are white and 2 out of the 5 balls are red. Now it says that when we take the ball out the first time, we are not going to put it back in without replacing the first ball, it says. So if we chose a white ball the first time, it's not in the box when we take the second ball out. So the second ball is either white or red, but now only 2 out of the 4 balls that are left are white and 2 out of the 4 that are left are red. Now let's go to the second possibility. Maybe we didn't take the white ball out, maybe we took a red ball out the first time. So if that's what happened, that means when we're ready to take the second ball out of the box, we have 3 out of 4 that are white and 1 out of 4 that's red. So now let's think about our probabilities. What we're looking for is the probability that both balls taken from the box were red. Now we could multiply the probabilities along the branches to get any probabilities, but the one we're really interested in is this one at the bottom, which is getting a red ball the first time and the second time. So if we multiply those probabilities, 2/5 times 1/4 is 2/20. That would simplify to 1/10. So the probability that both balls taken from the box are red is 2/20 or 1/10. So we'll alter this problem just a little bit more. A random ball is taken from this box, its color is noted, and then it's replaced in the box. Then a second ball is taken from the box. What's the probability that both balls taken from the box were red? Now if you read this carefully, you'll see we've only changed one thing in the problem, and that is once we take this first ball out, we are going to put it back into the box. So let's see how that changes our tree. This part isn't going to change. The first ball is either white or red. 3 out of the 5 balls are white, 2 out of the 5 are red. But since we are going to put that ball back in, that means even though we take a white ball out, the white ball is going to go back in. So when we get ready to take the second ball out, the probabilities are going to be exactly the same as they were for the first draw of the ball. We still have 3 out of 5 that are white and 2 out of 5 that are red. And in fact, if we had taken the red ball out the first time, we would put it back in, and now for the second ball, we either have white or red, and once again, the probabilities haven't changed because the balls are exactly the same. 3 out of 5 are white, 2 out of 5 are red. We're looking for the probability that both balls taken from the box were red, which is at the bottom of the tree, the path that goes through red and red. That's 2/5 times 2/5, which is 4/25. So let's look at one more type of problem that involves probability. And this has to do with looking at how probability relates to geometry. If a dart is randomly thrown at this dartboard, what is the probability that the square is hit? So we're really looking at area here. We're looking at what the probability is that we hit a part of this dartboard that has a certain area. So in order to figure out what the area of the square is in relation to the whole area of the dartboard, what we're going to do is subdivide this dartboard a little bit more so that we have some equal parts we can look at. Because as it is, the dartboard does not contain parts that have equal areas. So we'll just make some more cuts in this dartboard and look for some ways that we can have pieces that are the same size. And that should do it. If you look very carefully, what we've got is a whole bunch of triangles now on the board that are exactly the same size. So if you count up the total number of triangles on the board at this point, these small triangles, you'll see that there's 16 of them, and 2 of the 16 are making up the square, that green square on the board. So the probability that we would throw a dart at this dartboard and hit the green square is 2/16 or 1/8.